Alrighty, y'all. Today we're taking a look at dynamics, homework 2, custom problem number 2. And I'm going to be deriving how the process for which we're going to be dealing with all of it, right? So we're going to start, we're given our ER vectors, and every unit vector I put a hat. Any non-unit vector I will do a line. But that's going to be cosine of 2t, sine of 2t, and then the transpose of all of that. And then e theta again is negative sine 2t cosine of 2t, right? And then we're trying to find the velocity and acceleration of p of t, right? That's a vector, right? Given this position is 2t plus 1 er plus t squared plus 5t e theta, right? So t is our independent variable, right? So what we were talking about a bit in recitation, right, is if we have some vector, let's call this vector p again. Actually, no, we'll use a different one. We'll use a capital R, right? Here's our R vector, is some magnitude of R in the ER hat direction, all right? So what we do when we're taking the derivative of this function, right, because this is our position vector, right? So when we take the derivative to get our velocity, right, we have r as a function of time, right? This is going to be some r of t, and this is going to be e hat r. And right, we know that e hat r is going to change with time because it's not always going to be pointing in the same direction, right? So if we take our derivative, right, our velocity is going to equal, right, a function of time times another function of time, and we're derivatizing, taking the derivative with respect to time, right? So we have to use our product rule, so that's going to be our r times, or r dot, right, derivative of the first times the second, e hat r, plus the first times the derivative of the second, so that's going to be d that dt, right? Because we're taking the derivative with respect to time. Well, right now, in our problem up here, we can find our derivative with respect to time because we have this in I and j components and x and y components. But right now, we don't know this with respect to time, so I'm going to pull this off to the side. Right, we're going to try to figure out what der hat dt is, right? So we know that our der hat, right, d theta, we take the derivative with respect to theta, that gives us our, these are not equal, right? Or this equals e theta hat, right? So if I put this up here, right, that's going to give us e theta hat, right? But now if we do, right, but we want this with respect to time, so we want time as our denominator, so we're going to do, to make it cancel, dt d theta, right? Theta cancels out, it's going to leave us with our d theta, right? And we know that this, dr dt, right? And we know that this is equal to this, right? So all this is going to give us is, right, the derivative of theta with respect to time, theta dot times e theta hat, right? So we get that our velocity is our r dot e hat r plus r theta dot theta dot e theta hat, right? Which is what we derived this in lecture the other day, right? And this is in the textbook too, right? So really we're applying the same principle here of using our product rule to funk around with all this to over this, right? Because we have a function of time multiplied by, right, ER is a vector function of time, right? So if we're taking the derivative with respect to time, right, so we're getting our velocity, that's going to be derivative of this, right? So I'm going to start with this. This is going to be our product rule, right? Derivative 2 times the other, right, plus 2t plus 1 times r d e hat r dt, right? And this time I can't just plug in whatever d theta dt is, right? Because I don't know d theta dt, and I know e theta hat, but I don't know what theta is, right? So I can find our derivative with respect to time in terms of this, right? Because if I just take the derivative of this with respect to time, it's going to just be, right, so d e r hat dt is going to equal negative 2 cosine 2t 2 cosine 2t, right? So that's our, I'm going to pull that more out of the way, right? There's our derivative of that with respect to time. Wonderful. And we're still adding, right, this. We have to product rule this now, too. So it's going to be 2t plus 5 times e hat theta plus t squared plus 5t times d e hat theta dt, which again, we're going to have to take the derivative of this with respect to time. So I'm going to do that real quick. d e hat theta dt is going to equal, negative sign is going to be negative 2 cosine 2t. Ooh, I did this one wrong, sorry. This one's supposed to be sine up here, my bad. Negative 2 cosine 2t and negative 2 sine 2t, right? So that, if we plug in all of this mess, right, we can plug this in too, because this is just going to be a vector in the I, this is in the I hat, and this is in the j hat direction, right? Those are rectangular coordinates. Plug that in here. That's your velocity vector. Take the derivative again, right? Now we have this times this in product rule, and this times this in product rule, this times this in product rule, this times this in product rule. And you're going to have to take another derivative of each of these. It's doable. It's just going to be a lot of terms for your acceleration vector, because obviously product rule is going to keep splitting it. So I'm not going to give you the whole answer because academic integrity, but let me know if you have any more questions about this or anything else that you want me to try to explain, and I will do my best to try to explain it, because I guess Sydney explains stuff.